morning. This is Dr. Shankaraiah, Associate Professor in Department of Physics. I'm going to discuss today about Introduction to Quantum Mechanics. So, before going to discuss about quantum mechanics, we should know what is the problem with classical mechanics or classical physics. So, classical physics was successful until 19th century. In the beginning of 20th century, there are problems with classical physics, and hence there is a new branch that is called quantum mechanics has started. Okay, so until 19th century, the classical physics was successful, and it basically had three branches: Newton's laws of classical mechanics, Maxwell's electromagnetic theory, and thermodynamics. So these three branches were able to explain all the phenomena that occurred around us in nature until 20th century. So the first branch of classical physics is Newton's laws of classical mechanics. So Newton's, there are three Newton's laws. Basically, the first one is first law of inertia, second law of force, and third law of action reaction. So using Newton's laws of motion, we can study the dynamics of matter. We can predict or study the dynamics of matter. That means at x equal to 0, at time t is equal 0, after a certain time, where will be the particle or an object? We can predict the dynamics. So the matter is treated as particle in classical physics. So treating matter as particles, we study the dynamics of matter using Newton's laws. So let us see in detail what are these laws. So the first one is law of inertia. A body continues in its state of rest or motion in a straight line unless acted upon by a force. That means if you do not apply any force on a body which is in rest or in motion, it will remain in rest or in motion until upon there is a force. So this is first law of Newton's, which is called law of inertia. So the example is, you can look at the example, shake up a bottle of ketchup and keeping the bottom down and then stop. So then you will find that ketchup comes out of the bottle because of this inertia. So the second law of Newton's is law of force or law of momentum. So that states that a body acted upon by a force moves in such a manner that the time rate of change of momentum equals to the force. That means if you apply force on a body, it will move. So there is a momentum, and that momentum is directly proportional to the force. So take the rate of change of momentum, and then you will find the force that is acted upon by a force. So we are applying some force on a body and it is moving, right? So this force which we applied is equal to the momentum dp by dt, where p is the momentum. So this example, take two stones of different masses and apply same force on the two stones. Then we will find that the stone with less mass will travel only less distance, will travel higher distance compared to the stone with higher mass, because the force which we applied is same on the two stones which have different masses. So F is equal to m into A, right? So F is equal to m into A, which is equal to m into dv by dt. So where v is velocity, or you can write this as dp by dt also. So the force that we apply is equal to the rate of change of momentum. That is Newton's second law, which is called as law of force or law of momentum. The third law of Newton's is law of action reaction. So that states that for every action, there is equal and opposite reaction. Okay, so example is hitting the wall with your fist. You hit the wall with your fist and you will find that you feel pain because the force which you applied, there is a force from the wall. So the force which we apply, action, is equal to the reaction from the wall. So that is why we feel the pain. Whatever force, if you apply more force, then you will feel more pain. So that we can understand from this law of action reaction of Newton's. So that is about Newton's classical mechanics, where we treat matter as particles, and we study the dynamics of matter using this Newton's laws of motion. Now, the second branch of classical physics is electromagnetic theory. So Maxwell's have proposed many laws in electromagnetic theory. Here we discuss some of them. The first one is Gauss law of electric field, and Faraday's law of electromagnetic induction, and Ampere's law of magnetic field. So these are some laws that we discuss in this electromagnetic theory, where we treat radiation as waves. We will discuss in detail what are these laws. So in the classical mechanics of Newton's, we treated matter as particles, and we study the dynamics of matter. So here in electromagnetic theory, we are treating radiation, for example, heat or light. We are going to treat it as waves to understand the radiation. So the first law of Maxwell electromagnetic theory is Gauss law. So Gauss law states that the net flux of an electric field in a closed surface is directly proportional to the electric charge enclosed by the surface. That means, so if you have a force, so there is a force, there is a charge Q here. Q is a charge. This charge is enclosed in a closed surface. So the net electric field that is generated by this charge is equal to the amount of charge you have in this closed surface. So that is Gauss law of electric field. So you can see the applications. Some of the applications are given. So second law is Faraday's law in electromagnetic theory. It states that an electromagnetic force induces and thereby a current flows in a closed coil if there is any change in magnetic flux through the coil. Okay. So if there is any magnetic change in the magnetic field, we will find that there is a current flows that through the coil. Okay. So I have a magnet here. So S is south pole and N is north pole. Okay. And I have a coil here at a point A. At a point A, I have a closed coil and I applied magnetic field to this coil. And we will find that at a point A, there are many magnetic flux lines that are passing through this coil. Right. So when we move this coil to the distance A prime, then we will find the number of flux lines that are passing through this coil is less, 1, 2, 3. So that means there is a change in the magnetic flux lines when you move this closed coil from A to A prime. Whenever there is a change in the magnetic flux line passed through this coil, we will find there is a current flow that we'll find in this closed coil. So you can see some applications of this Faraday's law, which transformers, electric motors, generators, and credit card, which we use in our daily life. Okay, so coming to the third law in electromagnetic theory, which is Ampere's law, and it states that the magnetic field created by an electric current is directly proportional to the size of electric current. Okay, so in the previous statement, Faraday's law, we discussed that if there is any magnetic change in the magnetic flux line, we will find that there is a current in closed coil. Now, Ampere's law, we are saying that if there is a magnetic field that is created by electric current, okay, if there is a current that is passing through this closed coil, current is flowing in this closed coil, this will generate magnetic field. Okay, so the magnetic field that is created by this closed coil or closed charge or current flowing in this coil is directly proportional to the electric current. How much electric current is, or how much charge that is passed through this coil. The magnetic field produced by this coil is directly proportional to the amount of current that is passed through this coil. So some of the applications are given here. So the third branch of classical physics is thermodynamics, where this we use to study the interaction between matter and radiation. So in the first Newton's laws of motion, we discussed that we treat matter as particles, and in the second electromagnetic theory, okay, let me write it down here. So new classical mechanics, okay, so classical mechanics, we said that we are going to treat matter as particles. Okay, this is the first one we studied. In the second one, we discussed that that is electromagnetic theory. We said that we are going to treat radiation as waves. What do you mean by radiation? Heat or light. Heat is nothing but radiation. Light is nothing but radiation, right? So we are to understand the dynamics of matter. We are going to treat matter as particles in classical mechanics of Newton's, and we are going to treat radiation as waves. Suppose if you want to study anything about the dynamics or properties related to heat or properties related to light, we are going to treat this heat or light as waves. So all these and the third branch of classical physics is thermodynamics, where we study the interaction between matter and radiation. Okay, so these are the three branches of classical physics which were successful in explaining all the phenomenon occurring around us until 20th century. Okay, so now we will discuss about laws in thermodynamics. So there are four laws in thermodynamics, starting with the zeroth law of thermodynamics. It tells that discuss about the thermal equilibrium. It provides a basic for property called temperature. Okay, so if we consider three objects which are in thermal contact, we will find that if A and B are in thermal contact, we will find C is also, for example, like this. Okay, so that is discussed, I think, in the next slide. Okay, so I'm going to discuss about this zeroth law of thermodynamics. So that says that if so A and B and C, so this is A and this is B and this is C. So I'm going to keep A, B in thermal contact. Okay, so I'm going to measure the temperature of A, which is T1, and I'm going to measure the temperature of B, which is TA, this one, and this is TB, and then so I'm going to keep C is also in thermal contact with B. Then I'm going to find that TA, the temperature of A, is equal to temperature of B. And finally, I am also going to find temperature of A is equal to temperature of C, and temperature of B is also equal to temperature of C. So this is the statement of zeroth law of thermodynamics. So the second one is about first law, which tells us about the conservation of energy. That means you cannot create energy or you cannot destroy energy. It's totally conserved. Second law discusses about the entropy. Entropy is also a form of energy, and okay, so that is about second law. Third law discusses about the absolute temperature and entropy score. So this is just revision of these four laws of thermodynamics. Okay. So classical physics, all these three branches were explained properly up to 20th century. But in the beginning of 20th century, the classical physics failed basically in two domains. So the first one is relativistic domain. Okay, so where we, for example, where we treat bodies with moving with the speed of light. Okay, so second one is microscopic domain, which is, for example, structure of atom or molecule. Okay, so these are the two domains where classical physics failed to explain some experimental results. Okay, so basically here we discuss about the experiments microscopic regime. So these are the four experiments. So black body radiation, photoelectric effect, atomic stability, and Compton effect. So these are the 4 experimental results that could not be explained by the classical physics. So we've discussed what are these, starting from black body radiation. So what is this black body? We know that in any object, general object, if you take, it might absorb some and reflect some of the radiation, but black body is a material object that absorbs all the radiation that is falling on it. Okay, so black body is a perfect absorber as well as perfect emitter. So how do we construct a black body? So we have discussed black body is an object that is going to absorb all the radiation that is falling on it, and it is going to emit all the radiation radiation that absorbed when we gave energy, right? So how do we construct such a black body? So black body, we can take a hollow cavity. So this is a hollow cavity. So this is a hollow cavity, and we are going to create small hole on this hollow cavity, okay, through which we are going to supply light into this hollow cavity. Okay, so this light is going to get absorbed by this walls of this hollow cavity, which is going to act as a black body. So we are giving light through this wall, and then all this light is absorbed by this black body through continuous reflections at the walls of this hollow cavity. So it absorbs all the radiation which we are giving in the form of light, and when we heat this black body to temperature T, it is going to behave as a perfect emitter. That means whatever light it absorbed, it is going to emit all the radiation that absorbed when we supply light. So black body emits thermal radiation on heating, right? So the radiation or the heat energy that is emitted by the black body U is plotted on y-axis versus frequency on x-axis. So x-axis is basically frequency, y-axis is basically heat energy. Okay. So we find that we are heating the black body to different temperatures. So we at a temperature 2000 Kelvin, you see there is continuous distribution of this form. When we heat the black body up to 3000 Kelvin, this is the continuous distribution, and at 4000 Kelvin, this is the continuous distribution of heat energy emitted by black body for different frequencies. And this is the continuous distribution of heat energy that is emitted by the black body at 5000 Kelvin over different frequencies. Okay, so we find that whatever temperature we are heating the black body, it is emitting the energy, and all these are in the form of continuous distribution. So this continuous distribution of heat energy could not be explained by the classical physics. What is the problem with classical physics, and why could not explain by this classical physics? For example, to understand or to explain this continuous distribution, Stephen Boltzmann proposed a P is the power emitted by this black body, which must be equal to approximately equal to fourth power of temperature. Okay. Similarly, Wiens explained the heat energy emitted by this black body. So U is the heat energy, which is roughly equal to exponential minus beta nu by kBT. Okay. So Wiens theory could explain only half of the continuous distribution of heat energy emitted by this black body. Similarly, Rayleigh jeans also proposed their theoretical heat energy emitted by this black body, and their Rayleigh jeans formula could also explain only other part of the black body distribution. Okay, so there is no continuous distribution of black body using both this Wiens energy distribution and Rayleigh jeans energy distribution. So all these theoretical predictions are treating radiation as a wave, right? So by treating radiation as a wave, they could not explain the continuous distribution. They could explain only part of the distribution, but not the full complete distribution of black body. So Planck said that, okay, Planck postulated that energy of radiation emitted by these oscillating charges must be integer multiples of h nu. Okay, so E is the energy emitted by this black body must be integer multiples of h nu, and where h is the Planck's constant and h nu is the energy of a quantum of radiation. So we are saying that Planck said that, okay, don't treat radiation as a wave, instead treat radiation emitted by the black body as set of particles. Okay, and each particle is called as quantum, and each particle is going to carry an energy h nu, where n is the integer. So there can be two particles, n is equal to 2h nu, n is equal to 3h nu, three particles that are emitted by the black body in the form of discrete number of quantum or particles. So we Planck postulated that, okay, don't treat radiation as wave, instead treat radiation as quantum, which is going to carry an energy. So classical physics, we treated radiation as waves, and in quantum theory, we treated radiation as particles. So we could successfully explain this black body radiation by treating radiation as particles, which is given by the idea which is given by Planck. So this idea started the new branch of physics, which is called quantum mechanics. So the data that is given by Planck theory was exactly falling on top of this is experimental curve of heat energy emitted by this black body. So these red dots are the theory, Planck's theory. And the solid black line is Planck's experiment. Okay, so Wien's and Rayleigh-Jean's laws could not explain the continuous distribution where they have treated radiation as waves. Planck's law could explain the continuous distribution properly where Planck treated radiation as set of energy particles which are called as quanta. So the next experiment that could not be explained by this classical physics is photoelectric effect. So this experiment is carried by Hertz, where he considered a metal and he irradiated the metal with light, and he found that electrons are ejected from this metal. And he found that if the frequency of the incident radiation nu is smaller than the threshold frequency nu naught, no electron can be emitted irrespective of the intensity. And if nu is greater than nu naught, number of electrons ejected increases with intensity of the light but does not depend on the frequency. Okay, so there is a threshold frequency nu naught. If the frequency of the light which you are giving irradiating the metal frequency is less than threshold frequency, there will be no electrons ejected. And the kinetic energy of this ejected electrons depends on frequency nu, but not the intensity of the light beam which we are giving. And the kinetic energy of this ejected electrons increases linearly with frequency of the light which we are given. So as per classical physics, any frequency with sufficient intensity would be able to free electrons from metals. But here we are finding that electrons are not ejected, even though if you increase the intensity, only electrons are ejected only when the frequency is greater than the threshold frequency. So these are the experimental results of Hertz. Okay, so this is as per classical physics, if a metal is irradiated with weak source of light, an electron would keep on absorbing energy at a continuous rate until it gets sufficient energy to leave the metal. Okay, if this is true, it takes hours for an electron to leave from the metal. Okay, but this disagrees with the experimental result of Hertz. So in experiment, increasing intensity alone does not help in ejecting the electron from a metal. So these experimental facts indicate that concept of gradual accumulation, continuous absorption of energy by the electron as predicted by classical physics indeed wrong. That means even if you are giving a weak source of light with high intensity, the electrons will not be able to eject. So this photoelectric effect is experimental result of photoelectric effect is explained by Einstein, where he assumed that light is made up of particles, each carrying an energy h nu, which is called a photon. When a beam of light of frequency nu is incident on a metal, each photon transmits all its energy h nu to electron near the surface. So Einstein said that okay, the light which you are irradiating on this metal, don't treat this light as wave as per classical physics. Don't now treat this light as set of particles, which is called as photon, and each photon is going to carry an energy. So photon is entirely absorbed by this electron. So the electron that absorbs energy in the form of quanta, irrespective of the incident radiation. So Einstein explained this photoelectric effect where energy of photon is h nu is equal to work function W and the kinetic energy K. So the energy of photon is taken by the electron, that is used in the form of work function, that is nothing but the energy required to dislodge electron from metal, and the remaining energy used as kinetic energy for the electron. So using this new Einstein theory, he could explain the Hertz experimental results that the kinetic energy of the ejected electrons is linearly increasing with frequency. So classical physics also could not explain the atomic stability. We know that atom consists of nucleus and electrons. There is attraction between positive and nucleus, positive nucleus and negative electron, and if this because of this attraction, atom should collapse. But we find that atoms are stable in nature, and as electron is revolving around this nucleus, electron experiences a centripetal force. Okay, so an accelerated charged particle emits energy, and as it emits more and more energy, this atom should collapse. But we find that atoms are all stable. That means that classical physics is not able to explain the atomic stability by treating energy emitted by these electrons is in the form of wave. Following Planck's quanta concept and Einstein photon concept, Bohr's model for hydrogen could explain successfully the atomic stability of energy. He argued that atoms can be found only in discrete states of energy. The emission or absorption of radiation takes place in the form of discrete amounts like photon or quanta, which is of energy h. So this Bohr's model could explain successfully the atomic stability, which tells about that atoms are stable. So we have discussed about blackbody radiation, photoelectric effect, and atomic model. These are the experiments in the microscopic regime that were not able to explain by the classical physics branches. For example, Newton's classical mechanics and electromagnetic theory and thermodynamics. The reason is that the classical physics, all the three branches of classical physics treat radiation as a wave. Radiation is treated as a wave. And similarly, matter is treated as particles in classical mechanics, physics. But now we find out that from Planck and Einstein and Bohr, we found out that radiation can also be treated as particles and matter can also be treated as waves. Okay. So in the next lecture, we will discuss about can particles behave as waves. So now we find out that radiation which used to be treated as waves, now we have started treating radiation as particles. So the next one, matter which we are treating as particles, can we treat this matter as waves? So that is the next question which we answer in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.